Thank you, Dean. And thanks to Phil for inviting me out and getting this set up. And a special thanks to War Games, who sponsored my travel in getting me here. Today, my talk is going to be a little different than my usual talks. So if you expected one of my usual talks, sorry to disappoint. But today I want to talk about generic programming. And there is a reason for that. This is a quote from Alex Stepanov. You cannot fully grasp mathematics until you understand its historical context. And this year is a special year for generic programming. Right. And here's why. 1988. So when I was at CPPCon, they had little icebreakers that you were supposed to put on your badge as you were walking around, you know, a question or a statement that would invoke conversation. So mine was how old is generic programming? And the answer is 1988. The best response I got when I told somebody, oh, it was 1988, is, and I bet some people in this room are thinking this right now, was, oh my gosh, that's an entire year before Taylor Swift. Right? So what was going on in 1988? Number one song was Faith by George Michael. Number one movie was Rain Man. The Winter Games were being held in Calgary, so yeah, Kate's going, yay, Calgary. U.S. Senate ratified the INF Treaty between the U.S. and Soviet Union, so Ronald Reagan, for at least most of the year, was still president, along with Mikhail Gorbachev. George H.W. Bush won the U.S. presidency. At this same time, I was working as a system software engineer at Apple Computers. So I always say I worked at Apple between jobs, which means I joined Apple. Yeah, you guys get the joke. I joined Apple right after Steve Jobs has left, and I left Apple just before Steve Jobs came back. So I worked at Apple between jobs. And this paper was published, Generic Programming. So to be fair, the term generic programming had appeared once before this paper, the year before, in 1987. It appeared as a forward reference, though, to this paper. So I'm counting this as the anniversary for generic programming. So in all rights, Alex Stepanov should probably be the person giving this talk, but Alex is retired now. Never cared for public speaking before he retired. So even though he gives wonderful talks, he's not going to give this talk. So I'm going to give this talk. Alex wrote this paper. You see he's not even listed first in the credits here. This is Dave Musser. He's a professor at RPI, and he wrote this paper with Alex. And there's a picture of Alex. That's Alex when he worked at Adobe with me, and the papers behind are a printout of Euclid's Elements. And so Alex is a big history buff and a big fan of Euclid. And so if you ever wonder where the title of the book, Elements of Programming, came from, it's from Euclid's Elements. So this is a quote from the paper. And I think this pretty much nails generic programming. Right? By generic programming, we mean the definition of algorithms and data structures at an abstract generic level, thereby accomplishing many related programming tasks simultaneously. The central notion is that of generic algorithms, right, which are parameterized procedural schemata that are completely independent of the underlying data representation and derived from concrete, efficient algorithms. So that's the definition of generic programming that holds today. Okay? But it didn't start with this paper, right? What led up to this paper? So from 1976 to 1987, Alex had been working on this idea. This is Alex a little before 1976, born and raised in Moscow. So this picture was taken in Russia. So in 1976, Alex had a job interview to work on a parallel system. and he was nervous. He actually knew nothing about parallel programming, had never done any threaded work up to this point. And he got sick, food poisoning the night before, and was running a fever. And he claims while he had this fever, he realized this. Now, this wasn't something unique to him, something that was known, but he realized that there was a relationship between parallel computation and the associative property, right? So by associativity, we mean a binary operation on a set S is called associative if it satisfies this requirement, basically that you can reorder things for calculation, right? So basically what his dream was informing him was that parallel reduction is associated with a mathematical concept known as monoids. Right? A monoid is a data set that has an operation that's associative on it. But Alex generalized this, and he thought, there's something fundamental here. It's not just about parallel computation, but it's about software in general. That software is somehow associated with algebraic structures. And that kind of sent him down this path. At first, he thought, the right way to do that is to come up with a new programming language where we can talk and reason about software in terms of algebraic structures. So he worked with Dave on a programming language. This paper was published in 1981, a language for manipulating generic objects called Tecton. Tecton is still kind of kicking around. Dave Musser continued the work on this for years. It's a language around formal methods and proving systems. Okay, so the third author listed here is Deepak Kapoor. So that's a picture of Deepak. And then Alex moved on to apply some of this. So he wrote a couple papers here. One called Higher Order Programming. So you start to see a little bit of a theme going on here. And another using tournament trees to sort. Both of these were with Aaron Kirschenbaum. Aaron is a graph theory expert. Okay? And the language in the papers was scheme. But Alex credits working with Aaron for his realization that arrays were important. And scheme is a functional programming language. You would typically define things recursively. And it was Aaron that said, no, that's nice for scheme, but actually having random access into an array is important. So Alex credits Aaron for that realization. Right? And that brought us up to 1987, and Alex worked briefly at Bell Labs. And this was a bit of a game changer. So first he started a friendship, which has become a now 30-plus year friendship with Bjørn Strustrup. They're still very good friends. He also met Andrew Koenig, and Andrew explained to Alex the beauty of the C machine, right? That the C machine was not a hack, that it was a beautiful construct in its own right. And Alex read a lot of code by these guys, Ken Thompson and Rob Pike. Everybody knows who these folks are. So creators of Unix. Ken Thompson, I think, is one of the most brilliant software engineers of all time. He ranks in my top 2 computer scientists of all time. He's also the person responsible for UTF-8 encoding. For years, he held the title of the creator of a chess program that was the best chess program on the planet. And he kind of came out of nowhere in that, where he saw a computer chess tournament and was like, you guys are doing it all wrong, and sat down and won. And he's very much the father of the Unix system and was working at Bell Labs when they were working on Multics. And again, he had this realization that Multics was too complicated and going the wrong direction, and created Unix. So that had a huge influence. Something else happened. So Alex is a trained mathematician. He was a professor briefly before he left the Soviet Union. And Alex discovered the works of Euler. Do people know who Euler is? Right, so Euler, this is a picture of Euler, 18th century mathematician, physicist, engineer, astronomer, kind of your all-around Renaissance man, even though a little later than the Renaissance here. And Alex credits his reading of Euler with what he calls de-Borbicizing him. He was de-Borbicized. Does anybody know the reference for Bourbaki, right? Alex will say this frequently, and he kind of expects that a room full of people would understand what he means by it, and nobody gets it. It's a reference to Nicolas Bourbaki, who is not actually a person. Nicolas Bourbaki is a pseudonym for a group of French mathematicians from the 1950s who set out to rewrite all of the foundations of mathematics in very abstract terms, and this is where set theory comes from, is from Bourbaki. And so if you've ever heard the term new math, right, if your parents complained because you were learning new math and this was the mathematics that they didn't understand, new math comes from Bourbaki, right? So what does it mean to be de-Borbicized? So one of Euler's central tenets was that knowledge is founded on the basis of precise quantitative laws. Okay? That is to say that mathematics is about discovery, about what is, not about invention, about what you wished it were. Right? So this is a philosophical shift in Alex's thinking about mathematics. And this changed his understanding of software to say that software is not somehow related to abstract mathematical structures, but rather that software is defined on algebraic structures. All software is. Good software is. Bad software is. Right? And the idea of understanding software is understanding what the algebraic structures are, what they are, concretely, that these are the things that govern the way the machine works. And so learning to write software is a process of discovery, not a process of invention. Right? And that brought us back to 1988. And he wrote this paper. Now, honestly, I did not read this paper in 1988. Had I read this paper, I don't think I would have been that impressed. Okay? In retrospect now, I'm very impressed. It is a brilliant paper. But this is the main code example in the paper. You can't quite see it, but this is an implementation of partition. Let me see if I can blow up some pieces here. Okay, so it's an implementation of partition, which you might recognize from the STL. The language here, if you don't recognize it, is Ada. Okay, so Alex was working in Ada at the time. You see some things that look familiar. We have coordinates instead of iterators. S is a sequence. This is kind of a generalized sequence. We've got a middle, which is an out coordinate. So this is going to partition and return the out coordinate. But we have this middle OK out parameter, which is a Boolean. Anybody want to guess what middle OK is about? No? So the challenge here is in Ada, typically you would describe a range as a closed range as opposed to a half-open range like we do in STL, right? So the FL here is specifying a closed range. And so we're finding the partition point. But that means our partition point, we need to know whether or not it's on which side of the partition, okay? So the Boolean there says whether or not our midpoint is true with the predicate, okay, for our partition, or false, right? Right? And you have to have that because you have the boundary cases at the end. Okay? So the code here is actually, relatively complex for what it is. Oh, I lost my pointer. Get the right pointer here. So the code is relatively complex, and it's a little gross here. You see this function called test? That's not an argument coming in. It just assumes that there's some global test function hanging out there to determine whether or not that's your predicate for your partition. It's not passed in, it's just some global function hanging out there. Right? So it's not quite what we would see in STL. But nevertheless, Alex and Dave wrote an entire book on algorithms, and if you looked at this book, you would find many of the same algorithms that you would find in STL, but this is for the Ada generic library. So this was a precursor. Now, here's why I wouldn't have been very impressed. So in this same time frame, like I mentioned, I was working at Apple. I was not doing C++ work at the time, but I was aware of C++. This is a copy of my actual book that I picked up probably in 1987, so probably a year before this. And at that time, I was working on a QuickDraw system. This is a copy of my original Inside Macintosh. This was the promotional edition, which predates a few years. You can see I read it just a few times. This is a description of the QuickDraw coordinate system from Inside Mac. This was done by a guy named Bill Atkinson, pretty famous guy. How many people have heard of Bill Atkinson, one of the original Macintosh guys? Right? So this is a quote from that book, talking about the QuickDraw coordinate system. It says, all grid coordinates are integers. All grid lines are infinitely thin. These concepts are important, exclamation point. They mean that all elements represented on the coordinate plane are mathematically pure. Mathematical calculations using integer arithmetic will produce intuitively correct results. If you keep in mind that the grid lines are infinitely thin, you'll never have endpoint paranoia. Right? The confusion that results from not knowing whether the last dot is included in the line. Okay? So one of the things I did while I was at Apple was I rewrote a piece of Bill's code for regions. Regions are a two-dimensional interval set. So it's basically a two-dimensional structure of half-open intervals. Okay? And it's a compact form to represent an arbitrary shape, right? And Apple had a patent on this, and they considered it a trade secret. At the time that I was working on it, I couldn't tell anybody about how the code works. Now you can go to the Computer History Museum and download the code if you're interested. The code was written in 68,000 assembly language, so it wasn't even in C or Object Pascal, which was the two languages that I worked mostly in at the time. It was 68,000 assembly language. But this was a beautiful piece of code, right? The reason why I was rewriting it was to remove some of the 16-bit limitations so that it could work better with larger data sets, and so bumping things up to handle 32-bit sizes. And it was really well architected and a beautiful thing to go in and look at. And it was the first time where I read a piece of code and realized that there was kind of this underlying notion of truth and beauty that could exist in a piece of code, right? And I kind of got what he was talking about it being mathematically pure, right? These days, I never get pushback on this concept. This is a slide from one of my other talks, an algorithm I developed. And this is, I think, this slide probably first appeared in my C++ seasoning talk from Going Native years ago. Nobody ever complains these days when I draw my pointers to not point at an element, right? A lot of people don't catch this. I always draw my pointers, right, like here, F, P, L, to point between elements, okay? We're dealing with half-open intervals. That's the way I think about algorithms and I think about ranges. The pointer doesn't point to the first element, it points before the first element, right? Right. So this was the the gather function. That's what it does, right? And the result here is a pair of pointers between elements. When you're working on algorithms, this makes it a very nice and clear way to think about things. Right? Right? And there's a fundamental reason for this, right? If you have a sequence of n elements, there are n plus 1 positions in that sequence. Now, today, we don't even think about that very often, right? The thinking of half-open ranges is kind of burned into our psyche. A lot of that comes from STL. It wasn't invented in STL. It existed before that, right? Bill Atkinson knew before that. Ken Thompson knew before that, okay? But it certainly wasn't popular at the time. Right? Which brings us all the way up to 1993. During the 5 years here where we're skipping over, Alex worked on other projects, other things, did not have a chance to do generic programming, and then he found himself at HP Labs and an opportunity to get back into generic programming. What's going on in 1993? Number one movie is Jurassic Park, right? A big CGI movie. There was the bombing of the World Trade Center in New York. Bill Clinton was sworn in as our president. And the hot video games were Doom and Myst at that time. Right? For me at this time, I had left Apple. I had joined the Photoshop team at Adobe, which is where I'm kind of back, looping back on my career. I think if I end up back at Apple, I'll complete the palindrome. So I'm now working kind of back in graphics with the Photoshop team. And Alex resumes his work on generic programming. And Andrew Koenig, who we knew from Bell Labs, suggests writing a standard library proposal, right? Because the standard library needed, the C++ standard library here, needed some notion of containers and algorithms, right? And Alex had already written a book with Dave on Ada, and Andrew knew that, and so Andrew was like, you know, you should do this for C++. We could use that proposal. And that brought us up to 1994. And this is truly an amazing piece of work, right? The standard template library. To think that it took 1 year to write this is absolutely phenomenal when you think about the pace of things going into the standard library today. How long has it taken us to get ranges or modules or concepts? This was a phenomenal piece of work, right? And Alex gives a huge amount of credit to the creation of this to Meng Li. That's a picture of Meng. It was very hard for me to find a picture of her. There's a picture in an old Dr. Dobbs article that came out at the same time. The article is online, but not the artwork from it. So I could not find that original picture. So I sent Meng an email, and she was kind enough to send me a picture. She said this was from roughly 1995, a picture of her. And Alex basically says that the standard template library would not have happened without Meng's assistance here. Dave Musser, in fact, who had been Alex's longtime collaborator, did not think that this was a possible endeavor. He thought it would be a lot of work and ultimately rejected. The library that they had done for Ada had some limited amount of use, but not nearly what they were hoping for with Ada. And so Dave thought that this was kind of a fool's task to go off and do this. So he did not go after that. It's not to say he didn't participate. Kind of late, he did the implementation of STD maps and the balanced tree implementation. So that came out of Dave kind of late in the game. But Meng was the driving force here. She thought that this was something that was worth doing. She kept Alex on track and organized, and if you know Alex, he needs somebody to collaborate. He will run off on tangents. And she added a huge amount of polish and structure to this effort, putting it together. So to understand why this is important, we're going to go back in time again, all the way back to 1983. This is an article from John Bentley titled Programming Pearls. Okay? And it was actually a series of articles in the ACM. This one was on writing correct programs. Just a little hard to see up there, so writing correct programs. Okay. That's a picture of John. So this article contains this quote. So he says, I've assigned this problem. He's talking about a problem of writing a binary search in courses at Bell Labs and IBM. So we're not talking about run-of-the-mill programmers, right? We're talking about professional programmers at major companies. So the programmers had a couple of hours to convert the description of a binary search into a programming language of their choice, right? High-level pseudocode was fine. 90% of the programmers found bugs in their programs. And I, John, wasn't always convinced of the correctness of the code in which no bugs were found. Okay? How can that be? This is binary search, right? Well, one of the guys who I worked with for a lot of years, still at Adobe, we occasionally collaborate together, said this: I want to hire the other 10%, right? If 90% of the people can't write a binary search, I want to hire the 10%. When I joined the Photoshop team now 25 years ago, after going through interviews, I was handed a one-page sheet of paper with a description of a problem. It even said on here, this is a problem for a binary search. It's a particular binary search. Take it home. Spend as much time as you need, okay? With the caveat that we're looking at other candidates while you're taking time. So we may hire somebody else before you get your answer in, okay? But take as much time as you need. You shouldn't reference outside resources, but there's nobody babysitting you, so you could, I suppose, if you wanted to. Write a piece of code to solve the problem, and write an argument. Does not have to be a formal proof as to why you believe your code is correct. Okay, so it's a test both of your coding skills and your writing skills. Okay. I passed the test, I think barely. My code was not that pretty. But after I joined the team, I got to read a lot of code that other people submitted. Now, you wouldn't think that this is that hard. That's a picture of Mark Hamburg, who came up with this idea. We still use this test today. If you join the Photoshop team today, you will be handed the same sheet of paper that I was handed. Right? So that's 25 years. And I can tell you the submissions have not improved a great deal, surprisingly. Right? So this was the code. I translated this into kind of modern C++ that John Bentley published in the book. John Bentley actually put the answer in the book in pseudocode. I wanted you guys to actually be able to read this. But I think that this is an accurate translation, and in fact, John has published on his website his own ports of the same algorithm to C, and so this is at least very true to his own port to C. Okay, so this is his answer to binary search, right? So we've got an array of n elements, and we're trying to find some value v within it, and we're going to return the index of where we found it. So the first thing we notice is we say, oh, well, if our range is empty here, we're going to return -1. Okay, so immediately that means we need assigned values here. We need some flag, right, that we can return. Now what we're going to do here is we're going to find our midpoint. There is a serious problem with this line of code. Anybody see the serious problem? One person here?
L plus U could overflow.
Yeah, L plus U could overflow. Okay, so this potentially overflows. Okay, so down here we do our comparison. If it equals, we return m. Now we have two comparisons there, okay? So we're checking to see if it's less than, and we're checking to see if it's equal to, right? It's only necessary to have one comparison. This, most people think when writing a binary search, is an optimization. I should stop as soon as I find it, right? But you're paying an extra comparison at each level of the search so that you can short circuit the search. You're better off just doing one comparison and going all the way until you find the minimum point. So then we have this line of code where we adjust our L and U, our lower and upper bounds, where we adjust our upper bounds to be m minus 1. What's a potential problem here? Anybody? So what can happen here is the subtraction of 1 can end up with -1, okay, again. So we can underflow here if we were using unsigned values. Luckily, we're using signed values. And the way this algorithm works is we end up returning -1 if we don't find the object, okay, which is throwing away work, because ideally, if we were able to if we failed to find the object, we would return the position of where the object would go, okay? But all of this code is dealing with a closed interval, which makes that a difficult thing to do, right? So this is John's solution in the book. And this kind of stood as the gold standard for how you would write binary search for all the intervening years, right? And it's not a great answer. So I'm working on Photoshop, and Alex has published the paper on STL and the open source, the HP implementation of STL, and it's generating a little bit of buzz about this library. And I think this would be an interesting thing to incorporate into the Photoshop code base. But at that time, it was very rare that you could find a compiler that actually implemented exception handling, and Photoshop had its own exception handling scheme that was based off set, jump, long jump, and a bunch of macros. So in order to use an external library, we had to review the code and retrofit it to make sure that it would work correctly with our exception handling system. So I download the HPSTL and make it my job to read through every line. It's not that much code within the STL to understand it and to retrofit it if necessary to work with our exception handling system. And I find this. This is an implementation of lower bound. This is a binary search. In fact, this is a correct answer to the Photoshop take-home test. Okay. This is actually a beautiful little piece of code. Okay, so first it's doing a binary search. It takes a half-open interval coming into it as opposed to a closed interval. It's a generic interface, so we're not just finding an int in an array, right? We're finding anything within almost any type of sequence, right? It works for forward iterators, it works for random access iterators, works for bidirectional iterators, right? So I could do a binary search on a linked list, and there's actually reasons why you would want to do such a thing. It does not overflow, okay? So it's very careful and precise about its mathematics here. It only has a single comparison in here. It has one return statement, and it's returning, right, the position where the element would go if it doesn't find it, right, or the position of the element. This is a beautiful piece of code. But it wasn't just this piece of code, right? At this point, I've been reviewing people's submissions for binary search. I can say that I had only ever seen one submission that was this beautiful prior to me seeing this, and that was done by a physicist he wrote a beautiful piece of code. He actually wrote it in Algol, of all things, and submitted a formal proof with it. We made him an offer. He did not accept, unfortunately. And I run across this. But it isn't just this piece of code, right? If you go through the rest of the STL, it is every algorithm in there. You have to kind of strip out a little bit, right? There's all this junk for compilers and double underscores for symbols and all the template header crap. You have to look at the algorithms, right? All of the algorithms are carefully constructed, right? One of the main algorithms inside of STL is stable sort, and it's an in situ stable sort. And not that long before the STL was published in Knuth's Art of Computer Programming, an in situ stable sort that was solvable in polylog n time was rated as an open exercise, meaning that there was no known solution, right? And Alex has this beautiful little solution in there for stable sort that builds it up out of all the other algorithms. All the algorithms within the STL fit together like puzzle pieces, right? I saw this and I thought, who writes code like this? Okay, right? I mean, keep in mind here, I'm working with a bunch of phenomenal engineers, right? Great people. These are some of the top people in the industry. And I've never seen somebody who writes code like this, okay? This is not like the code that Alex published in his paper 5 years before, right? He's clearly grown and had some time to think about it. So it's just this phenomenal piece of work. And for me, it was like I want to write code like that. How do I write code like that? So now we're going to skip ahead a little bit here to 1998. Okay, and this happens, right? The C++ ISO standard. And it includes STL, which was a phenomenal accomplishment, right? The STL within C++ 98 standard looked nothing like container and algorithm libraries at the time, right? If you looked, everybody knew that when you had a new container class, you had to use inheritance, and the algorithms had to be member functions on the class, and things were concrete and not generic. And yet this happened, partially because of Alex's friendship with Bjarne and with Andrew Koenig, right? So that's the C++ Standards Committee, right? Now, also in 98, there was a workshop on generic programming. And I think one of the critical papers that came out of the workshop was this from Dave Abrahams. That's a picture of Dave. How many people know who Dave is? A few people. So Dave was also one of the principals when the Boost library started up. It was Beam and Dobbs' idea, but Dave kind of drove a lot of it and ran with it. Dave kind of left the C++ community a few years ago to become one of the principal designers on Swift. So he's been doing that. And what is this? Exception safety and generic components. So this is where the rules of exception handling come from about the basic exception guarantees and the strong exception guarantees, and that the standard library now follows. And this was Dave's work to figure out how exception handling would work with the standard library. And just a few moments ago, I told you, right, I had to review the code to make sure that it would work with Adobe's, with Photoshop's exception handling mechanism. And that was actually when you got into the containers and what happens if a constructor throws and things like that. That got pretty hairy if you go back to the old HP code base. And I thought Dave did a brilliant job of kind of moving the problem into a mathematical setting where you could come up with a set of guarantees and you could actually reason about generic code in the presence of exception handling. So this was a fairly seminal piece of work. This paper also got published. This was co-authored by Alex Stepanov and this guy, James Dennert. The fundamentals of generic programming. Okay. So this paper was important for two reasons. This line, we call the set of axioms satisfied by a data type and a set of operations on it a concept. Okay? So before that, Alex had already referred to them as being, to concepts as being things like algebraic structures, akin to algebraic structures. In his early work, they were just called algebraic structures, but he deviated that somewhat because mathematics doesn't have a notion of complexity, and he thought that in computer science, you're dealing with physical properties, and so the structure itself has to encompass the complexity of the operations. So that's why we're not talking about just an algebraic structure here. Okay? And so they decided they needed a name for it. Alex isn't sure. I had a conversation with him a couple weeks ago whether or not the name was coined by himself or by James or by Dave Musser. He thinks it might have actually come about a little before this in the conversation he had with James Musser and just got written down here. But nevertheless, this is where, when we talk about C++ and concepts, this is where that idea originated, was in this paper. The other thing that happened was this quote, and this is the first place where we see the term regular type and a regular type defined. Okay. So the idea of a regular type had already kind of existed in STL. I always say whenever you see a capital T in STL, what Alex meant there was a regular type, but it hadn't really been formally defined what that meant. And so this paper defined what a regular type is. And this came out after the 98 standard, right? And yet this is still part of our regular lexicon now in C++. And now we can skip ahead a little bit to 2002. So what happened in 2002? So Alex had been promoted. He was a VP at Compaq and chief scientist at Compaq. And when I talked to him at the time, he said basically he was kind of in charge of mergers and acquisitions. He wasn't really in charge of engineering anymore. Compaq itself was being acquired by HP, so Alex was about to loop back in his career to HP. But this guy, his name is Larry Musser. He had worked with Alex at Bell Labs and had gone to work in Adobe's research group. And at that time, I was also working in Adobe's research group. And so I was friends with Larry as well, still am friends with Larry. And Larry invited Alex to come to Adobe and give a talk, right? So Alex comes and he gives a talk loosely about STL. And after the talk, I strike up a conversation with him. And we end up going up to my office so I can show him what I'm working on. And we probably ended up talking for at least 3 hours, maybe 4 hours, just chatting away. And at the end of the talk, Alex says, you know, I really wish that I could do this again, that I could just be an engineer again. And I said, why don't you? Okay, well, about 2 weeks went by, and my phone rang. I pick it up, and it was Alex. And he said, so I thought about what you said, and I decided I want to go back and be an engineer. Are there any positions open at Adobe? Okay. So I did manage to get him hired into a group. He got fired from that group. He got rehired, and I was told that a condition of his rehire was that I be his boss. So that's how Adobe Software Technology Lab came about in a very short summary. And we ran the Software Technology Lab for just about 8 years, right? And so I was Alex's boss longer than anybody in his entire career, which is quite the accomplishment, I think. The acronym is very deliberate. So when Alex did his work on STL, that was done in Hewlett-Packard's Software Technology Lab, which is why it's actually called STL. And people have also said, you know, STL stands for Standard Template Library. Sure. People have also said it stands for Stepanov and Lee. bit of a stretch, but okay. So this was very much an homage to the HP Software Technology Lab, where STL came from. So while Alex is working in the Software Technology Lab, he's teaching a set of courses to the Adobe employees. And one day he is bemoaning to this guy. His name's Greg Gilly. He was my boss at the time. So Alex is bemoaning to Greg that he's done all of this work on generic programming and nobody understands it, right? Nobody gets him, type of thing. And Greg makes the comment, of course not, you never wrote it down. Okay? So that sets Alex off to write a book. The first big draft of this book, possible to see the title here, Notes on the Foundation of Programming. You can download this from Alex's website. This was a collaboration between Alex and somebody else on my team, Matt Marcus. That's a picture of Matt and Matt's son Kai. We also referred to this book as PAM, which stood for Programming as Mathematics. And so we got to the point where the book was maybe 2/3 complete. And Alex and Matt had a strong disagreement about direction, and that turned into a bit of a blow-up, and the book was scrapped. Quite unfortunate. But that led to Alex switching his collaboration to somebody else on my team, somebody named Paul McJones, and that led to this book, Elements of Programming, with Alex and Paul. There's a picture of Paul. How many people know Paul for anything other than this book? Okay, so nobody. One person up here. So Paul's a great computer scientist in his own right. He worked at IBM with John Backus. He worked with John Backus on System R, which was one of the first relational databases. He worked on Modula 3, which was a language to be a successor to Modula 2. So he's a brilliant individual in his own right. And he and Alex set out to write this book. How many people have seen this book? Many of you. If you don't, after this talk, go on Amazon, buy a copy of this book, work your way through this book. Emphasis on work. This is not a light reading book. It's only about 200 pages long, but it is a math text, right? It is a math text about programming. And so it's going to be a struggle. There's lots of theorems and lots of exercises to prove the theorems. It's a beautiful book. This book is very much the encapsulation of what is generic programming. It's also notable for one particular reason. The term generic programming never appears anywhere in this book. Anybody have a guess as to why? So Alex was a bit discouraged at the time when he sat down to write this book. He thought that the term generic programming had come to mean something other than what he intended it to mean, right? That somehow generic programming had become associated with type and category theory and with metaprogramming. Right? Because the STL used metaprogramming, but the STL wasn't about metaprogramming. It just happened to use some metaprogramming as a means to an end, right? And so Alex thought that generic programming had come to mean something else, and he didn't like what it had come to mean. And so this book was him distancing himself a little bit and trying to go back and say, no, this is what I meant. So this is one of the algorithms from the book. This is one of the partition algorithms. It's a semi-stable partition. It's developed within the book. And if you go back and you compare this algorithm to the original partition algorithm in the old Ada book, you can kind of see how far along things have come. And for one thing, this algorithm, you see how it's built on top of other algorithms. We have find and find if not in here, putting the pieces together. The other thing of note is this line right here, requires, right? That didn't exist in C++, right? Not yet. That line. So here's an appendix from the book. I guess this gives me a Strostrup index of 1. So Bjarne and I wrote this appendix for the book. It's 7 pages in the book. It describes the language used within the book, and it describes it. The opening paragraph here says this is a subset of C++ used in the book. Well, that's actually a lie. It's not a subset of C++. It's a bit of a different language in its own right, okay? It includes things like requires. Types within this language are at the same level as objects. So in theory, within this language, you could write code to manipulate types in the same way that you would write code to manipulate objects. So it would be completely legitimate in this language to iterate over all the members of a struct, for example. Okay? I happen to think it's a fairly beautiful little piece of work that we put together. So down here is where you see the grammar for constraints using require clauses, right? Now, concepts within the book are not described within code. They're described as mathematics. So in elements of programming, this is the description of a concept, okay? So we have a mathematic notation to describe concepts, much in the same way that you would describe an algebraic structure in mathematics. And that brings us up to 2006. And this paper, Concept Linguistic Support for Generic Programming. Okay, so now there's a growing effort to put concepts into C++. And there were actually 2 independent efforts going on to do this. There was the Texas A&M effort led by Bjarne Strostrup and his team. You know, Bjarne was a professor at Texas A&M, for people who don't know. And Andrew Lumsdaine, who was a professor at Indiana University, and his team. They had done lots of work in things like the Boost Graph Library and lots of interesting work in generic programming. And so these are some of the people here. This is Doug Greger. Doug Greger wrote an implementation of concepts in this time frame for GCC and later left to work on Swift. This is Jaakko Järve. Jaakko was a professor at this time at Texas A&M, and Jaakko's the person who is responsible for lambdas in C++, C++11, and he wrote the lambda library for Boost. This is Jeremy Seek, who had done much of the work on the Boost Graph Library out of Indiana. This is Gabrielle Das Reis. Gabby is now responsible for doing the module work in C++. And Gabby worked with Bjarne at Texas A&M. And this is Andrew Lumsdaine. I like this picture of him. This is him in a guitar workshop. He likes building guitars. But he was the lead of the team at Indiana University. And we already saw a picture of Bjarne, and so Bjarne is one of the other co-papers on this. So this paper was these 2 teams trying to come together. They had 2 competing proposals, and the standard committee had said, we don't know what to do with this. You guys have 2 different views of the same system. We don't know how to move forward. You guys are the expert. Get in one room, come up with a unified proposal. So this was the unified proposal, a huge amount of work, and very contentious between these 2 teams. And 2011 came about, and of course, because these guys had come together and created this unified proposal, it was very successful, right? I mean, now we have concepts in C++ 11. No, we don't. It basically collapsed under its own weight, right? So that brought us to 2012, right? There's a bit of disappointment. We did not get concepts into the language. This seemed to be a very important thing. So at this point, Alex has moved on from Adobe. Software Technology Lab, unfortunately, is no more. I had already looped around. I had left Adobe with the destruction of the Software Technology Lab, worked at Google on Chrome OS for a year, and I had found myself back at Adobe a little more than a year later. And Alex landed at A9, which is a subsidiary of Amazon. So he was working in A9. And Alex hosted a workshop over at A9, which has become known as the Palo Alto Workshop. And this is the Palo Alto report that came out of that workshop. So there's a large number of people, most of them names you might recognize. But the one person who I'm going to call out here, besides Bjørn Strustrup, is Andrew Sutton. This is a picture of Andrew, and so Andrew is now the kind of the key driver of concepts for C++ 20. What was important about this workshop is Alex and myself and Paul said, you guys are making this too complicated. We wrote the book, or at least Alex and Paul wrote the book, Elements of Programming, and we kind of showed that with relatively simple language construct, with just constraints on functions, you could get a huge amount of the benefit of all of this complexity that people are arguing about. So could we strip concepts down to that, to what we did with Elements of Programming? And that's what became known as Concepts Light, right? And that's what has led to the current C++ 20 proposal for concepts, right? So we end up in 2015, and Alex writes this book with Daniel Rose. There's a picture of Daniel. Okay. So I am going to call out something at this point. If you notice, Alex gets a huge amount of credit. He's certainly a common thread here. But for engineers, I want you to realize that there's not a single paper, there's not a single piece of work in this entire presentation which is Alex Stepanov alone, right? Computer science is a social aspect, and I think requires conversation and differences of opinion. And if Alex had done all of this work on his own, I don't think we would have what we have today. Every one of these people contributed and shaped what became and what we know of now as generic programming. Okay? And Daniel Rose here came along and said, you know, you did this work called PAM, this previous book, and I like that book, and you never published that book. And we should kind of pick that up and complete it. So there's a huge amount of credit given at the front end of this book to Matt Marcus and the work that Alex had done with Matt on the PAM book. This book I'd also recommend getting and reading. This is a much lighter read, right? At least I think it's a lighter read. I probably read this twice in a week, and I'm a pretty slow reader. That's an exaggeration, but it is also a bit of a history book. So it follows the evolution of algorithms from Pythagorean times and from Egyptian times, and how algorithms evolve into generic algorithms and ties that all in with generic programming. And I think creates the setting that generic programming is mathematics and follows along in the tradition of mathematics and fits in with the evolution of these fundamental algorithms through time. So here you get to learn some wonderful algorithms and meet some great historic mathematicians and find out their history and what problems they were trying to solve, real concrete problems of the time, and how that led to generalizing existing algorithms and evolving them along the way. So it really is a beautiful book and a very nice read. The other thing notable about this book is you say, now we're using the term generic programming again. And that's because Daniel Rose had an argument with Alex and said, you know what? You need to reclaim this term, right? This is yours. So take ownership of it. And so I'm very thankful to Daniel for doing that. So that brings us up to 2016. This is when Alex retired. So this is a picture of Alex's retirement party. He's loosened up a little bit. Occasionally I can get him to talk tech just a little bit. He lives with his wife and one of his sons in Palo Alto, and we go up and have lunch on a fairly regular basis. But he prefers to talk about history and politics and anything other than programming these days. So that's why he's not here giving this talk. He's a bit out of it. So now we get to zoom into the future, 2020, right? And I think now we actually have a shot. This is the working draft standard. And down here in the middle, what have we got? We've got constrained templates, right? They look actually quite similar to what we have in Elements of Programming. So this is a big part of Concepts Light, and I'm pretty pleased with the direction this is going. And so my biggest fear with Concepts is there are still various factions who want more, who want pieces of what we had in the Indiana proposal and pieces of what we had in the Texas A&M proposal. And I'm kind of hoping we don't. I want to see us take this baby step and move it forward and learn from this step and keep it as light as possible and get it out the door and get experience. Okay. And so that brings us up to today. I want to close on a bit of a quote here. So this is from an interview with Alex. Generic programming is about abstracting and classifying algorithms and data structures. It gets its inspiration from Knuth, who I would rank as #2 greatest computer scientist, or #1, depending on what day you ask me, right up there with Ken Thompson, and not from type theory. Okay, meaning it's Euler, it's not Bourbaki, right? Its goal is the incremental construction of systematic catalogs of useful, efficient, and abstract algorithms and data structures. That's the goal. And when Alex was having the conversation with Greg Gilly, where he said, nobody gets what I'm trying to do, I think this is the piece that still gets missed. Even after all the books and all the publications, when I go and talk, people will tell me, okay, well, I've got this algorithm, but I can't use one of the standard algorithms, right? And I will say, that's okay. The standard template library is not the beginning and ending of a catalog of all algorithms and all data structures on the planet, right? It's just scraping the surface. There's a huge amount of work to be done. Right? And we kind of treat the STL, it's a beautiful piece of work, as if it's both the beginning and the end. It's not the end, people. It's an example of where to go. It's an example of how you should be writing your code, right? And as an industry, I'd like to get us to the point where we had a place where we could go. This was one of the inspirations that came to Boost, is that there should be a place where you can go to find high-quality algorithms and data structures and to contribute to them, right? And they should be written with the same kind of precision that the STL is written, right? You should kind of have the proof to go along with that code, and these things should become trusted things. So that's the piece, I think, that gets missed. And so Alex closed it with, such an undertaking is still a dream, right? And I think it is. I think we've made a lot of progress, but I think we still have a long way to go. And so that's my closing. So that's my history, last 30 years of generic programming. Yeah, if people have questions, I think we started early. We still have time. Question over here.
So I'm interested in knowing what the core of the disagreements in the concepts library is about, what those missing pieces are. What's the kind of fundamental idea or thing that they're really trying to reach for that may not be really useful, but it's mathematically it might be more pure, or what is it?
Well, so the fundamental disagreement, if I can try to distill it, between the Indiana and Texas A&M teams were around whether or not the foundational mechanism for how you describe a concept was by example or through a new language construct by specification. Okay, so whether or not you could just write a piece of code that said this expression should be valid, or whether or not you had to define basically a function signature that said it must match this, right? So that's where I think the fundamental disagreement is. But then there's a huge number of other features that come into play. How do you declare whether or not a type models a particular concept? And since modeling a concept means it meets a set of semantic, not actually syntactic attributes, if you have something that is not a syntactic match, can you adapt it? Can you put in a model statement that says, this is how this type models this concept, right? This is the set of transformations that you would have to go through, right? So there's a huge amount of complexity that comes up when you start doing that. If you actually want to see the closest, I mean, you could go back and read the papers, but if you want to see the closest working system to the Indiana model, at least, go look at Swift and Swift protocols. Right, that's Doug Greger's work, who kind of left the C++ community after this whole blow up and went to work on Swift and continues to work on Swift to this day. And he took a lot of what he did for concepts and brought that into the Swift language. So,
think about generic programming. It always highlights algorithms and data structures.
Yep.
And I think it's easy to go online and find C++ programmers talking about that one really important abstraction that goes between them, that glue. And it wasn't mentioned in your talk, I think, at all, and that's iterators. Is iterators something that maybe is the one sort of essential part that hasn't really, that a lot of programmers don't get?
Yeah, so the question here is, we didn't talk about iterators in this talk. We pointed out they were originally called coordinates. Alex actually doesn't like the term iterators, but that was something that the standards committee had said. We don't have coordinates into data structures in languages. Nobody knows what that is. We have iterators. Is kind of the standard terminology. Yeah, I think iterators still are things that people don't quite get, surprisingly, because iterators are very much modeled after pointers. Within the C language. And they boil down, some people try to erase them, right? Andrei Alexandrescu went on a bend for a while to say, we should just deal with ranges and we should get rid of iterators. But this goes back to the basic concepts of generic programming, which is that iterators are the statement that if I have n elements, there are n plus 1 positions, right? An iterator is a position in the sequence, right? And you can't get rid of them, right? This was Eric and Niebler and I worked on the early stages of the ranges library, and I had to convince Eric, he gives me credit for this, that you can't get rid of iterators. You absolutely can't. And if you look at my gather function there where it's two stable partitions, and each stable partition returns a position, and the result of calling two stable partitions is those two positions form a range. Okay? If stable partition didn't return a position, right? If it returned a range, how do you do that? You need some way to combine two ranges that represent positions into a new range, right? Right? So you just cannot get rid of them. You absolutely can't. And yes, I think that people still struggle with that. And I think more people need to look at kind of my slides of using algorithms.
So I suppose this work's been going on for such a long time now, and I haven't read any of these papers, which I suppose gives some examples, but so my understanding is probably reflection will probably become one of the first flow-on effects of concepts, probably the most meaningful for me and perhaps my day-to-day job, but other than that, concepts for the average application engineer using C++, what does that mean for us?
Yeah, so, I mean, this is an interesting thing. So I think in general, concepts is going to just mean better error messages for most of the programmers. For those who are library writers who are trying to figure out what the algebraic structure is of what they're doing, concepts will be important. If you look at the history of mathematics, right, I mean, we have algebraic structures have names like rings and monoids and groups and semigroups, right? Those are the names of algebraic structures, right? As a mathematician, mathematicians don't go, hey, I know, I'm going to write a new algebraic structure today, okay? That doesn't happen. That's part of the realization with concepts light, which is we don't necessarily need a way within the language to define concepts. What we need is a way is to constrain functions to say that they only operate when a type satisfies a concept. Okay? We do need some way then to specify the concept into that, and so we need some very lightweight mechanism. But a concept, as we said before, is a relationship. For anybody who attended my talk last night, one of the fundamental things that I said is for any relationship, there's a corresponding predicate that goes along with that relationship. And we know how to describe predicates in code. And so I can convert my concepts into a predicate to say, does this type satisfy this set of relationships or not? And so I already know how to do that. That's just a function that returns true or false, right? That's what a predicate is. And so if I have that, and now I've got constraints, I've got most of what I need, right? And so I actually think that it's been this huge effort to get concepts surfaced up into the language. But as far as a language feature goes, hopefully they're relatively minor. Right? We're dealing with them kind of already, just informally.
Yeah, I had a question about what you said for concept in C++20, where you were saying that some people would like to go further. Were you referencing definition checking in concepts or something else?
Oh, I'm not going to get into all the things that I've heard. Basically, anything that's in the unified proposal or any of the two proposals that led to the unified proposal has been pitched in some form back to the committee, usually leading to an immediate argument. So yes, there's a huge amount of pressure to get more. Personally, I'm something who I want simpler and less. Right? I want more consistent and unified first. I want experience first. And so I'm like, no, we should have taken this baby step, in 2005, right? Somewhere in there. We should have had a version of C++ that had just the basic notion of concepts, and we should have started gaining experience. And So we're starting way late, but I want to see it small in a baby step.
One of the things I think you said was important to Alex was the time complexity properties of what he was doing. And we have that beauty. One of the things I liked about the STL when I first saw it was that you could reason about the complexity of how you were putting things together.
Yes.
But I've never seen anything in any of the concept stuff that addresses that aspect. Is that like one thing that is still completely missing?
Well, it's not completely missing. We tend to do it through kind of syntactic conformance. So, an example, incrementing an iterator, plus on an iterator, should be constant time. If it's not constant time, don't implement plus. But there's no, or I'm sorry, don't implement, shouldn't have just said increment addition, right? Advancing an iterator. So if you have operator plus on it, it should be constant time. There's no reason why I couldn't implement an operator plus on a linked list that was order n, okay? But we just say don't, okay? We say implicit in the operation plus is that it should be constant time. And if you don't care one way or the other, then we have a function called advance. Okay? So in that sense, we're associating the semantics with the syntactic form. We're associating the semantics of complexity with the name of the operation, with the name of the function. And so that's the approach that concepts within the language is going. It's not that complexity is not important, it's that we just associate it with the names. Conformance with the names.
Thank you, Sean. That was great.
Yeah.
I think for a lot of people, myself certainly included, that had a lot of nice things to add to the reading list. Other than adding to the reading list, is there anything that you want to say as, like, what is the homework that you wish everyone took away from this?
What is the homework? I think my homework is always the same thing, which is keep striving to write better code, right? Keep learning. I think STL was out there for a very long time, and most people the only thing they knew about STL was they had vector, list, and map, right? And that is not the point of STL. The algorithms are the point of STL, right? Go and look in algorithms. That's the point, right? Rotate, stable partition, stable sort. Those are the important things to understand and to understand how to use them. And I'm kind of hoping that awareness is rising up in the community. And so the takeaway homework is to say learn STL, not just at a superficial level, but as an example, right? And start to look at how do I write my code like that? How do I bring that level of precision and performance and predictability to the code that I'm writing, right? How do I do that? That to me is still the model.
I think this follows on relatively well. I work in a team where not many other people would write generic algorithms, and I see, or what I'm familiar with concepts, looks like it will make generic programming a lot more approachable. Do you have at the moment perhaps an easy introduction or another talk that you're familiar with that would help introduce what we're getting in C++20 with concepts that might assist me in introducing concepts to my team?
I probably wouldn't go straight to concepts. I would probably look at some of Eric Niebler's talks on the range library. Because range library is probably the first significant library that's written in terms of concepts. And so that would be where I would start, kind of come at it sideways and say, look, you have another algorithm library here that's a bit more approachable and that leverages concepts and puts all these ideas together. So that would be where I would probably start, I would think. If you just want to get a current state of the art in C++ concepts, then Andrew Sutton's CPPCon talk was pretty good. So, that'll be it, and that was our last question.
All right. Thank you very much, Sean.
Thank you.